Okay, now we want to go to the proof of Gauss's law, and we're going to use several of the examples that we've done before. So the examples we did before were not just done for the sake of an example only. No, they were going to help us in the derivation of Gauss's law. So one of the examples that we did before was we took a Gaussian surface and we put a charge at the center of the Gaussian surface, and we asked what was the electric flux through this Gaussian surface. If you haven't watched this video before, go and watch it and then continue. We proved that the flux does not depend on the radius. The flux just depends on the charge inside over epsilon naught. So when you take a sphere of a bigger radius, the electric flux is exactly the same. And we thought about this intuitively in the sense that the number of field lines going through the small sphere is exactly the same as the number of field lines going through the big sphere, and so the flux should be the same. And we proved it mathematically. The other result that we're going to use is, what if you have a surface like this one, and then you make an inclined surface such that it starts at one edge here and the other edge here, and the other two edges project exactly back onto the original surface. So that, again, intuitively, every line that goes through the back surface goes through the inclined surface. Mathematically, we proved it in detail. We showed that the electric flux through the inclined surface is exactly the same as the electric flux through the back surface. So if you haven't watched this video, go back and watch it first. So now let's look and see how we can reach the derivation of Gauss's law. We have a small sphere, the one in blue, and we have a larger sphere, the one in yellow. And look at what we're going to do. We're going to start a line from the charge, the center of the charge, and we're going to project it outwards so that it hits both spheres, and then make another line so that it also projects outwards and it hits both spheres, and then project another one so that we basically create an element of area on the small sphere and a projected area on the big sphere. So this area, the big area, is the projected area onto the big sphere. So the corner here projects onto this corner. The corner here projects onto this corner. The corner here projects onto this corner. And the corner here projects onto this corner. So do you expect that the electric flux through this small element of area would be the same as the electric flux through the big element of area or not? You can prove that it's exactly the same, actually. And if you want to think about it intuitively, the number of field line, any field line that goes through this small element of area has to go through the big one by construction, because we've made the corners here always project onto each other. So any line that goes through the small area has to go through the big one. So in the intuitive sense, the number of lines going through the surface is the same. You can prove mathematically that the electric field, since it goes like 1 over r squared, and you can prove that the area for this small element of area, it goes like r squared. So this is a smaller area, and when you go to a bigger sphere of a bigger radius, the area increases like r squared. When you multiply them, because the electric flux is the multiplication of the electric field times the area, then the r squareds cancel and you get a quantity that's independent of the radius. Okay, now, what if you don't have your surface to be the big sphere? What if it's a surface of any arbitrary shape? And you have to imagine that this blue surface here, the big one, it's an irregular surface of any shape. It's a three-dimensional surface, and the charge is inside it. It's not at the center because it doesn't have a regular shape. And this element of area here, the inclined one, is an element of area on that arbitrary shaped surface. This element of area is on the yellow sphere, and this element of area is on the small sphere. So now the question is, do you expect that the flux through the inclined surface is the same as the flux through this one? And look how it's projected. This corner is projected onto this corner, is projected onto this corner, and this corner is projected onto this corner, is projected onto this corner. If you think about the problem from the point of view of field lines, the flux should be the same. If you think about it mathematically, we showed before that when you have a surface that's inclined, that the flux through the inclined surface is the same as the flux through the back surface, as long as this inclined surface projects exactly back onto the original surface. intuitive sense, any line that goes through the small area goes through the big area on the circle, and it also goes through the inclined surface. So since the number of lines is the same, then the flux is the same. Okay, so that means that if you have a charge, and let's make a small sphere around it, and then you have your arbitrary surface also, so it's a three-dimensional surface. If you project outwards from the charge like this, so that the corner here and the corner here and the corner here and the corner here project onto the corners of the bigger area on the arbitrary surface, even though the direction of the area vector here is not in the direction of the electric field, and the direction of the area vector here is in the direction of the electric field, even though this is inclined with respect to this element of area, but the flux is the same. So that's what we just proved a while ago. And since the electric flux is the same, then the flux through the arbitrary shape completely will exactly be the same as the flux through the small sphere. But the flux through the small sphere, we know it. It's Q over epsilon naught. That means the flux through the arbitrary surface has to also be Q over epsilon naught. So we've just basically proven Gauss's law. That means that if you take a surface of any shape, it doesn't have to be a sphere, the flux, the total electric flux through this surface will be the same as the electric flux through a sphere, which means that it's going to be Q over epsilon naught. If you try to be clever and you make your surface, this is a cross section of the surface, you try to make the surface with curves like this, so you might say that the electric field line will go out and it won't contribute in a positive way for a positive charge. It won't. It'll always work out properly. Let's see. Because if you take a positive charge, when the electric field line goes out, it goes out with a positive contribution. Then it goes back in with a negative contribution, because the area vector here is pointing this way, from inside to outside, so it gives a negative contribution. And then it goes out again with a positive contribution. This one, this contribution and this contribution, they cancel each other out exactly. And so in the end, you still get a positive contribution to the flux through the surface. So it doesn't matter where you put your charge inside the surface. As long as the charge is inside the surface, and if it's a positive charge, the total electric flux through the surface will be positive.